Everything you touch today runs on this: your phone, your car, the traffic light that just changed, the card you tapped to buy coffee, the watch on your wrist, the router in your hallway, the thermostat you barely notice. All of it ultimately comes down to the same material. And it started as sand. Not lab-grown, not synthetic. Beach sand, the same stuff under your towel in July, the same stuff kids build castles out of without a second thought. But to turn that sand into the brain of a computer, it has to be purified to 99.9999999%. That's 9 nines, making it one of the purest materials humans have ever manufactured. Purer than surgical equipment, purer than the water you drink, purer, arguably, than anything else you'll encounter today, made or natural. One speck of dust the size of a virus can ruin it. One misplaced atom, a single atom out of billions, can turn a $10,000 wafer into scrap metal worth nothing. That shouldn't be possible at the scale we do it. Billions of times a day, in factories the size of small cities running around the clock, every day of the year. So how does ordinary sand, the kind you'd brush off your feet without thinking, become the single most important material of the modern world? Let's step inside and find out. Silicon is the second most abundant element in Earth's crust, right after oxygen, making up more than a quarter of everything under your feet. It's in nearly every rock, every grain of sand, every handful of dirt you've ever walked across, and yet almost none of it is usable. Not yet. The process starts with quartz, a specific high-purity form of silica sand mined in places like North Carolina, Brazil, and Norway, pulled out of the ground in open pits and hauled by the truckload to processing plants. Ordinary beach sand won't do. It's full of the wrong minerals, the wrong impurities, the wrong everything. Factories need quartz that's already around 99% silicon dioxide before anything else happens to it. And even finding deposits pure enough is its own industry. That quartz gets dumped into an electric arc furnace alongside carbon, usually coal, coke, or wood chips, and heated to over 2,000 degrees Celsius, hot enough to melt steel twice over, hot enough that the electrodes glow like something out of a volcano. Inside, a chemical reaction strips the oxygen away from the silicon atom by atom, leaving behind molten metallurgical-grade silicon, roughly 98 to 99% pure. It's tapped off in a glowing stream, cooled and broken into chunks like dark, glassy gravel. 98% pure sounds impressive until you learn it's not even close to good enough. For a computer chip, 98% pure silicon is like using tap water when you need distilled. Worse, actually, because at the electronic level, even trace amounts of the wrong element completely change how the material behaves. Every one of those remaining impurities has to go. What comes out of the furnace isn't a chip ingredient yet. It's just raw material for the hardest, slowest, most demanding stage still to come. Getting rid of the last 2%. This is where silicon goes from pretty pure to purer than almost anything else humans make. And it takes a process most people have never heard of, called the Siemens process. The metallurgical silicon chunks are reacted with hydrogen chloride gas, turning them into a liquid compound called trichlorosilane, a clear, volatile liquid that has to be handled with extreme care. That liquid is distilled over and over, boiled and condensed again and again, to strip out boron, phosphorus, and metal traces down to parts per billion. Concentrations so small they're almost meaningless to think about in everyday terms. Then the purified gas is piped into a sealed chamber and deposited atom by atom onto a thin silicon filament heated to about 1,150 degrees Celsius, glowing bright orange inside the reactor. Over several days, not minutes, not hours, days, the silicon slowly builds up layer by layer into a thick rod, like stalactites growing in a cave, except engineered, monitored, and controlled down to the smallest fraction of a degree. This method produces what's called polysilicon, and by the time it's done, the silicon is 99.9999999% pure. That's 9 nines. To put it in perspective, if a swimming pool's worth of water were that pure, there'd be less than a single drop of impurity in the entire pool. If it were a mile-long train, the impurities would fit in the space of a few grains of rice. And chip makers need every bit of that precision, because a single stray atom of the wrong element, sitting in exactly the wrong spot, can change how electricity flows through the finished chip and quietly ruin it. What was once beach-adjacent quartz is now polysilicon rod, pure enough to become a semiconductor, worth vastly more per pound than the metallurgical silicon it started as. But it still isn't a chip. It isn't even a crystal yet. And the next stage is where it finally starts to look like one. This next step looks less like manufacturing and more like something out of a glassblower's workshop, except the glass here is grown one atomic layer at a time, and it takes days, not minutes. Chunks of the polysilicon are melted down in a quartz crucible at around 1,425 degrees Celsius, just above silicon's melting point, held with almost no margin for error. A few degrees off in either direction and the whole batch can fail. A small seed crystal, no bigger than a pencil tip, is dipped into the molten silicon and slowly pulled upward while spinning in a method called the Czochralski process, named after the scientist who discovered it almost by accident a century ago. As it rises, molten silicon solidifies onto it in perfect atomic alignment, growing into a cylindrical ingot that can stretch over 6 feet long and weigh hundreds of pounds. A single continuous crystal, with every atom locked into the same repeating structure from one end to the other. This is, quite literally, the largest and most perfect man-made crystal most people will ever encounter. And it happens inside a machine, not a jewelry store, watched over by engineers making constant tiny adjustments to pulling speed and rotation. A single vibration, a single temperature swing, a single misalignment during the days-long pull can ruin the entire ingot, wasting all the time and material that went into it. The cooled ingot is ground down to a precise diameter, then sliced into thin, mirror-polished discs called wafers, each one thinner than a credit card. And now, finally, silicon is ready to become something with a brain. A finished wafer looks like a shiny gray dinner plate, but hidden in that surface is room for billions of transistors, switches smaller than a virus, packed in with a precision that puts anything else humans build to shame. This happens inside a clean room, a facility so controlled that the air has fewer particles floating in it than the air over the middle of the ocean, where workers wear full-body suits just to avoid shedding a single skin cell near the wafers. Each polished wafer is coated in a light-sensitive chemical layer, then exposed to intense ultraviolet light through a stencil-like mask that contains the entire circuit design, shrunk down thousands of times smaller than a human hair. Wherever light hits, the coating changes chemically, allowing unwanted material to be etched away with acids and plasma, layer after layer, sometimes over 100 layers stacked on a single wafer, each one aligned to the last with an accuracy measured in nanometers. In between, ions are blasted into precise regions to change how electricity behaves there, and metal wiring thinner than a strand of DNA is layered on top to connect it all. Millions of microscopic wires threading through a space you could cover with your thumb. A single modern chip can contain over 50 billion transistors, more than 6 times the number of people on Earth, packed into a space smaller than a fingernail. A single fabrication plant to make these wafers can cost more than $20 billion to build and takes years of construction before it produces a single working chip. The finished wafer is cut apart, tested one piece at a time, and the chips that pass are packaged and shipped out, while any that fail the microscopic inspection are discarded without a second thought. What began as ordinary sand from a quarry is now capable of doing billions of calculations every second, silently inside a device that fits in your pocket. That's how sand becomes silicon, silicon becomes crystal, and crystal becomes a chip, pure enough, precise enough, and small enough to run everything you own. 4 stages, each one more demanding than the last. A furnace hot enough to melt steel, a purification process so exact it makes a swimming pool of impurity-free water look easy, a crystal-growing machine that produces the most perfect man-made structure most of us will ever encounter, and a clean room precise enough to draw wiring thinner than DNA. Skip one step, get one temperature wrong, let one speck of dust land in the wrong place, and the entire chip is worthless. And yet it happens billions of times a day, in factories scattered across the planet, feeding an industry that quietly underpins almost everything modern life depends on. The next time you tap a screen, remember, you're touching a quarry refined 9 times over, shaped into a crystal, and etched into a brain smaller than your fingernail. Sand transformed into thought, until now. If this kind of hidden engineering fascinates you as much as it fascinates us, subscribe. There's a lot more of the everyday world left to take apart.